We left off in the previous video by talking about the naive and average methods of forecasting. So these models serve as baselines for future analysis. So in the absence of any trend or seasonality or cyclicality in our data set, these models will normally be okay. And so in the average model, the data for today is the previous period, or in the naive model, the forecast for today is the data from the previous period, and in the average model, the forecast for today is an average of n previous periods in the past, where 1 over n, you can think of that as a weighting factor. So if there are 3 periods, then each period counts for a third of the new forecast. And so this is an equal weighting. And so you can take a look at this method. I've applied it here. The naive forecast, I have Southern Company's stock price for 3 weeks in October, and the naive forecast is just that the price for today is the same as the price yesterday. So on October the 9th, I predict that it will close at 58.71, and that's because October the 8th data was 58.71. Now, I'm unable to make a 2-period average because I don't have 2 previous periods from the past, and I'm unable to make a 3-period average because I don't have 3 previous periods from the past, at least not in my data set. So I'm aware that Southern Company has data prior to October 8th, but it's not here on this chart. For October 12th, I have data from October 9th and October 8th available to me. My naive forecast is October 9th. That was 58.74. My 2-period average forecast is the average of 58.74 and 58.71, which is 58.725. My 3-period average does not exist because I do not have October 7th in my data set. So for the 13th, my forecast is 58.86. Why? Because that's the data from the 12th. That's the naive forecast. The 2-period average, I kick out the October 8th because I'm only using the previous 2 periods, so I'm using the 9th and the 12th. I have 58.74 plus 58.86. I take the average right in the middle, 58.80. And my 3-period average, now I include October the 8th in there because I need a 3rd period, so I average those together and I get 58.77. And we just continue to go all the way down the chart. Okay? And I need to fix this, got a 1/2 here. But we can evaluate the quality of the forecast with what's called error. And the goal of the forecast is to predict the future as accurately as possible. So we're going to utilize the errors of a forecast to evaluate its quality. Now, there are multiple ways to evaluate the quality of a forecast, but all of them involve comparing the forecast to the data. We're going to define the errors to be epsilon. Epsilon is the data minus the forecast. So it's the size of the raw miss. This could be positive, it could be negative. So I could under-predict the data, and that would be a positive error. I could over-predict the data, and that would be a negative error. So my forecast is too large. The percent error, I take the error and I divide it by the data. So think of the percent error as being a type of metric that you would use to describe the quality of your forecast to an external audience. I missed by 5%. I missed by 6%. And with percent, we're saying this is a percent of the value of the raw data. So it's a measure of the size of the miss that is framed in terms of the magnitude of your data set. So, when I say I missed sales by 3%, what we're saying is that, if we had 200 million in sales, then we missed by $6 million. Okay. And that could be too much or too little. So -3 would be an error that I over forecast. +6 would be an error that I under forecast, but I might describe it informally as 3%. And so We think of the error as being a method of evaluating the quality of the forecast, but I think of the percent error as being a method of communicating the quality of the forecast. And so once we calculate the error, we're gonna employ some method to aggregate the errors together to get a composite picture of forecast quality. And what I mean is we're gonna figure out how to incorporate all of the forecasts that we made into one coherent metric that tells us whether it tells us the quality of our forecasting method using some pre-specified criteria relative to some other forecasting methods that we could have employed. So this is the mode of comparison. We will be comparing multiple forecasting methods across this dimension. And this aggregation of the error is the dimension that we're going to choose. Now, this is not the only method that we could choose. We will look, hopefully, later on in the course at more complex methods. However, for this portion of the course, we're going to look at three different measures. One is called the mean squared error. So we're going to take all the errors, we square them. This is so that I'm not averaging together negative and positive errors. I square it so they're all expressed positively. We're going to add them together and divide by the number of errors that we have. So the mean squared error is 1 over n times the sum of squared errors. The root mean squared error is the square root of the mean squared error. Now it contextualizes the error measure at the observation level. And what I mean by that is that I can look at the root mean squared error as roughly the size of the average miss, noting that large misses are penalized more heavily. So once we square a large miss, that number is even larger, and that inflates the mean squared error, and it also inflates the root mean squared error. And so the idea is that forecast quality might very well be dictated by one large miss, and root mean squared error will capture that. And that's an important distinction to draw, because the third measure that we're going to look at, this mean absolute percentage error, where I take all the errors, I divide by the data. So I'm calculating a percent error for every error that I have. I take the absolute value, so I make them all positive. I then average that together. That is not penalizing any one miss any more heavily than any other miss. So if you miss by 10% and all the other errors are 2%, I'm just averaging a bunch of 10s and 2s. I'm not inflating the 10 by squaring it to 100 and inflating the 2s by squaring it to the 4. So, missing by 10 relative to 2 is 5 times as large, but missing by 100 relative to 4 is 25 times as large. So I'm not penalizing the miss by 10 in a quadratic sort of way with the mean absolute percent error. Okay, so let's just go back to the naive model. We're not going to use the root mean squared error and mean absolute percentage error right now to compare between models. Let's just work on the mechanics of calculating it. So the naive forecast for October 9th was 58.71, and it closed at 58.74. So my error, I take the closing price, 58.74. I subtract the forecast, which using the naive model was 58.71, and I have an error of 0.03. Now, if you square that, 0.03 is 0.0009. The percent error, if you take 0.03, divide it by the closing price, the actual data, 58.74, you will get 0.0005, which I express as 0.05%. So we missed by 0.05%. Now, the next data series is 58.86. That was the closing data for October the 12th. Our prediction was the October the 9th data of 58.74. So 58.86, the data, minus the forecast, 58.74 is 0.12. Square it, you get 0.0144. Take 0.12, divide by the data, which is 58.86, and you get 0.0020, which we say we missed by 0.2%. Okay, so now for October 13th, the closing price was a little bit lower. It was 58.34. And as a consequence, the forecast was too high. So we over predicted the closing price. 58.34 minus 58.86 is minus 0.52, so that's a negative, but when I square it, it becomes 0.2704. Now, I want you to note that 0.52 is roughly 4 times the size of the previous error, which was 0.12, maybe a little bit more. I think 4 1/3 times as large. But then if you take 0.27 compared to 0.014, you're looking at a magnitude difference of almost 20 times. Okay, and so even though the error is a little more than 4 times as large in absolute value as the previous one, the error squared is almost 20 times as large. Now, let's take a look at the percent error. It is minus 0.52 divided by 58.34. So that is minus 0.89%. And the relative difference in magnitude between the percent error and the error is very, very similar. Very similar. So this is a just kind of generic comment that we make here. Okay, so all of this is to say that the percent error can be calculated by taking the data taking the error divided by the data. Squaring the errors is calculated by taking the error and squaring it. So you do that. You add them all together for the mean squared error, for the squared errors, and you get a mean squared error of 0.373. The root mean squared error is 0.611. Look at 0.611 as being the average size of the miss accounting for the errors. Okay? And 0.73 is the mean absolute percent error, so about 0.7% miss. So the 0.611 represents an estimate of the average error accounting for large misses. Most of the errors are smaller in absolute value than 0.611, but there was a miss of 1.69 that caused our estimate to be quite a bit larger. The mean absolute percent error implies an error of about 0.43. So the error is smaller because it does not assign a quadratic penalty to large errors. And so I think baseline forecasts like the naive and the average model are important barometers that we can use for time series without trend, cyclicality, or seasonality. So these are the baseline forecasts. You come in day one for any time series that you have, you make these forecasts, you produce them, you take a look and see if these are acceptable for your organization. And if they are, you move on. And if they're not, then we have to go to plan B, which we will often be in plan B. These forecasts are very, very limited in what they can do. Okay, so in order to choose which forecasting model to use, we're often going to need to examine the time series via some graphical and quantitative methods. And graphing the data is important because these previous baseline forecasts will not be desirable for data with any trend, with any cyclicality, or with any seasonality in our data set. These are what we call persistent features, and any forecast that we make of the time series should try to capture these features. These baseline forecasts that we're talking about do not attempt to capture any of these features. So, it's also reasonable for a time series to have multiple features. So GDP is cyclical. But it also, you think of the business cycle, that's a macroeconomic concept. There are peaks, there are troughs. We go into booms, we go into busts. But, since World War II, GDP has been trending up. And so there is a positive trend with GDP, even though some periods it exhibits this cyclical behavior. Employment can be seasonal, but it could also trend up or down over time. So, you think of a retailer hiring for the holidays. Think of a department store. Now, some of these department stores have been trending up as far as who they hire over time, and some of them have been trending down, but every year around the holidays, they tend to trend up. So trend, what we mean by that specifically is that the time series is either increasing or decreasing over time. And so previous methods will be biased because they will not, since they only incorporate previous periods, they describe where the time series was, but they are not able to capture in real time where the time series is going, either good or bad. And so we're going to have to use different methods other than just the naive or the averaging model in these instances. And when we get to exponential smoothing, we'll talk about how we may need to look at different models there too. And so let's just take a look at trend in GDP, Georgia gross state product. So this is the time series that we graphed in R in class. The construction GDP is the red time series and the manufacturing is the blue. And you can see that over the last 8 years, both time series have been trending up. Okay, and so from 2010 to 2020, GDP was by and large increasing, especially in the manufacturing sector, but even you see it going up in construction, and any model should account for this. So even if we're trying to forecast the red time series, once there's this shift around 2013, we are going to miss the trend up the first time, but we should start to capture this trend going up going forward. And so that is an important concept because, as described previously, the naive model does not offer us the capability of doing this. And you can even see just kind of at a basic level that inability here. You can see we're always behind. We're always behind, and so you see a ton of positive errors for a lot of the time series. So what do we mean by cycle? The time series exhibits increases and decreases during irregular periods of time. So if you can time the cycle, it's not a cycle. It's a seasonal pattern. The seasonal pattern, the time series increases or decreases, but we know when it will increase and when it will decrease. Cyclical patterns are not that way. So cycles are irregular. They're often correlated with GDP if we're thinking at a macro level. In many of the time series that you're going to be interested in forecasting in a business forecasting class, you think of any type of sales or any type of revenue stream that your business has, it's likely to be pro-cyclical. When times are good, people buy more. It's unlikely. I don't want to say it's unlikely, but it would be very surprising to me to have you start out in a business that only deals with counter-cyclical products. For the bulk of the post-war period, we've been pro-cyclical. So it's difficult to make money consistently with a counter-cyclical type of strategy. Seasons are known; they're regular, days of the week, etc. So oftentimes we would like to deflate the forecast for low periods and inflate the forecast for high periods. So if you're thinking about restaurant revenue, you don't forecast the same amount of revenue on Saturday that you do on Monday. You deflate the forecast for Monday, you inflate the forecast for Saturday, and you may be doing it relative to a baseline of Thursday. Okay, where Thursday is a little more going on than Monday, but it's not quite as prolific as Saturday. And so we will talk about inflating and deflating the forecast with relation to seasonal behavior. But, going back to these time series features, we first have to identify whether it's reasonable to think that there even are any of these features. And so just to kind of take a look, we've identified some trend up. You can see trend up here. Here is cyclical behavior. This is consumer debt service payments as a percent of personal income. So how much of your income as a percent are you spending on paying off interest? And you can see that has been cyclical. Higher interest rates, about 6.5, then it falls when interest rates are lower, but it starts to shoot up again in the 90s, 2000s, then it starts to fall again, then it starts to rise again until 2020, and then people start paying off debt as we enter into this recession. So there's some cyclicality in this behavior. And we may want to try to capture that in our forecast. Now let's take a look at Amazon revenue. And you can tell I just took this revenue directly from Amazon and I put it into R and I graphed it myself. So I took this previous graph from the St. Louis Fed, but I graphed this myself, and you can see the obvious trends going up. Amazon's revenue has been shooting up, but there's also this seasonality in that every 4 quarters there's a spike. And so what's kind of interesting about Amazon is that their revenue has gone up so sharply that even though there's this seasonality in their revenue, it's still dwarfed by the rate of magnitude of the increase in spending. Okay, so just to kind of comment about how to make graphs in R, we talked about doing this in class. It's available on the other video, but you want to read it in via read_Excel or read_CSV. But if you have it in as an Excel file, the key with reading it in is that you have to tell R to read the data in as a date using column_type. So put a parentheses after, put C to concatenate, and then you have date as your first variables. That has to be the time for the time series. And then the subsequent variables are numeric. Then you create a t-symbol. You use the mutate function to tell R if your data are monthly, quarterly, whatever the case may be. You use the mutate function to tell R about the periodicity of the data, and then you use the as.t-symbol to define the data set in terms of its periodicity. And so these are all described in the previous video. However, I just want to point out that every time I want to go through and make a graph like this in R, I have to first go in the process, read the data in, make a t-symbol, and then graph the data set with autoplot. Okay, so a lot to take in, but some key features we're looking for are trend, cyclicality, and seasonality. And these features are not captured by the naive model or the average model, but they are things that we want to capture. So we've talked about graphical methods, just kind of looking, this is what we mean by season, peaks, valleys, peak, valley, peak. This is what we mean by cyclicality. Irregular troughs, peaks, valley, peak, etc. This is what we mean by season. Going up quarterly. Very defined. Very, very defined. So quarter 4 of 2014, quarter 4 of 2015, you can see quarter 4 spiking every time. Okay, this is not the only measure that we can employ to learn about the features of a time series. So a non-graphical method is what's called the autocorrelation function. It is RK. RK is the correlation coefficient, but the variable of interest is a lag of the past. So you can see it here. K is the number of periods between the current data and the previous period. So if I'm comparing the data from today to yesterday, there's just one period in between. If I'm going 2 days ago, there's 2 periods in between, etc. So the minimum for K is 1. And we cannot calculate an autocorrelation for the first value in our time series because there's no previous data. So that's why we start with K plus 1 and we start with time period 2 if we have a 1 period autocorrelation, time period 3 if we have 2 periods, etc. So think of it as in order to see whether the data are related to data in the past, you have to have that data in the past. And then we're just comparing the data that we have currently to the mean of the data and the data from the lag of interest to the mean of the data. So we compare these two numbers here. Then we add up and square just like the variance in the correlation coefficient. So a negative autocorrelation implies that the value of the current period is negatively related to the previous period of interest. So if the data are trending down over time, then if we have a large number of lags between our data and the start of the time series, we'll see a negative autocorrelation for those long lags because our data is really low relative to the mean, or the current data is really low relative to the mean, but the data from the past is high relative to the mean because the mean is in the middle. If we have data that are trending up, autocorrelations will be positive because when the data are low relative to the mean, the next period is also low relative to the mean. But if the data are high relative to the mean, then the next period is also high. So think of this as being like a measure of how related the data are intertemporally. You may see positive autocorrelations or negative autocorrelations representing seasons. So quarter 4 is positively related to previous quarter 4, so we may see a spike in the autocorrelation if we've got seasonality, and we may see some troughs when they're far apart. Positive autocorrelation, like quarters, negative correlation, different quarters or different months. So if we're comparing temperature, yeah, a good example of this is like average temperatures over time. There's global warming temperatures trending up over time. However, if we do a 12-month autocorrelation, we'll see that they're highly positively related. But if we do like a 6-month autocorrelation, we're comparing summer to winter and vice versa. We might not. We might get a negative autocorrelation. But in general, the data are trending up over time. Okay, so how do we calculate this autocorrelation? Let's just say we want to do a 1-period autocorrelation. So we have 5 periods of data. The data are trending down. 2, 1.9, 1.7, 1.4, and 1. So the average of the data set, we add these up. I have 8 divided by 5, that's 1.6. Now I compare the data from period 1 to the previous period. There is no lag. There's no ability to calculate autocorrelation, but I do include the first data set or data point in the denominator of the autocorrelation function. So I take 2, that's the data, I subtract the mean, I square it, that's the first one. Okay, and I'm going to do it 5 times because t is 5 periods. So I'm doing a 1-period autocorrelation. I start with period 2. I compare the data, which is 1.9, to the mean, which is 1.6. I multiply times the lag, which was 2, minus the mean, which is 1.6. So I have 0.3 times 0.4, which is 0.12. And then the data is 1.9, so this last column for the denominator is 0.3 squared, which is 0.09. Okay, so I go to the next period. The data is 1.7. That's the YT. We're in period 3, so I'm taking the data from period 3 minus the mean, which is 1.6. The data from period 2 minus the mean, which is 1.9, was period 2, minus the mean, which is 1.6. That's 0.3. So I have 0.1 times 0.3. That's 0.03. Now you can see that we have a negative here. I have 1.4, which is smaller than the mean, minus 1.6, which is the mean. That's minus 0.2. So I have a negative times a positive, which is negative. And I add all that up and I get 0.25. All right. That is the numerator. The sum of the denominator is 0.66. So my autocorrelation is 0.378. Okay, and what it means is that even though the data are trending down, there is a positive relationship between the immediate previous periods. Now here's the autocorrelation function for Amazon. You can see that this is related to the data that you see here. There's a high correlation between Amazon's revenue today and Amazon's revenue in 1 period in the past. So this is 1 period lag. This is a 2 period lag. This is a 3 period lag. This is a 4 period lag. And you can see that the gap between 3 and 4 is a lot smaller than the gap between 4 and 5 because Amazon's data are quarterly. And you see the same type of thing between period 8 and period 9. Autocorrelation, what that means is that the data that you see today is related to the data that you saw in the previous period. So there is what's called serial correlation of the data over time. Or the data are correlated with itself. White noise is a description that we use for data that have no correlation over time. So we just randomly generate some data. Here you go. The autocorrelation should be close to 0. And so we have a term for this called white noise. So just to summarize, we'll talk more about autocorrelation later on, but it is a measure of how data are related to each other over time, between time periods. So how much is the previous observation related to the current one? If there's a high positive autocorrelation, then if the previous data is low, our data will be low. If the previous data is high, our data will be high. If there's no autocorrelation, then if our previous data were high, it doesn't mean anything about the current data. If it's a negative autocorrelation, then if the previous data are high, ours will be low relative to the mean and vice versa. So if you see something that is like a zigzag pattern over time, the first lag will be negative, the second lag will be positive, and that's called white noise. And that's a description of the autocorrelation.